fossil fuels. I will delete it when I'm finished. So one of the things that we talked about last time is that for this to be able to work, light needs to be able to bend. So light has to refract. Let's go ahead and duplicate that. Okay, so light has to refract. So this means that anytime that we have some sort of energy, and remember that light is a form of energy, anytime that we're changing a medium. So if we're going from air into fluid, or we're going from fluid into a solid, that means that that energy is going to be refracted or bent or changed in some sort of way. So how many of you have had the experience of playing Marco Polo in the pool? I do not like going in the pool, but can somebody tell me what Marco Polo is? Is there anybody here who doesn't know about Marco Polo? Okay, so when you're in the pool and you're not underwater, so your head is poking above the surface of the water, your ears are above water, and you can hear somebody going, Marco, Marco, you can hear it, right? What happens if you go underwater? Are you able to hear as well? No. And part of the reason that that happens is that the sound wave basically loses some of its energy from having to travel from air into fluid. And that's why it's harder for you to hear things underwater. Not because you can't hear things underwater, you can, but when that original energy originates in air and it changes media, it changes into fluid or solid, it's going to have that bend to it. It's going to alter that energy. And that's basically what our eyeball is doing. So remember, I'm going to give you a quick little review. So last time that we were here, we were talking about the fact that if you have perfect 20/20 vision, that means that you are getting perfect refraction. Light needs to, are y'all okay over there? Is there anything I missed? No, I said perfect. Okay. So light has to refract perfectly. So there's a very subtle relationship between the different parts of the eye, the ratio of the eyeball's length. All of these things have to happen for you to have 20/20 vision. And one of the things that we kind of talked about is that judging from the fact that many of you right now are wearing glasses, many of you have what are called refractory errors. For whatever reason, that process has gone wrong in some way, and it is not, light is not refracting on the retina the way that it should. Now, I know that some of you are not wearing glasses, but raise your hand if you're like me today. Be in solidarity. Where are my fellow contact lenses wearers? Yeah. These are also ways to correct refraction that has gone wrong. So remember that if we want to be technical, what you and I call 20/20 vision is technically known as emmetropia. What? I brought 3 today. You knew that other drinks were going to get involved at some point. So as I kind of mentioned, the lens has a really special function here. It is going to be changing its shape. Hey, Sarah. It's going to be changing its shape to focus on objects at different distances. So for looking far away, the lens is going to need to stretch out. On the other hand, if we want to focus on objects that are closer to us, such as we might do for reading, the lens is going to have to fatten itself up. This process is what is known as accommodation. And one of the nice things about putting something on Zoom, ooh, they made some changes. I like it. This process that we're going to talk about a little bit later is known as accommodation. So basically, the lens is changing its shape to help you focus on different objects at varying distances. And one of the things that I mentioned last time is that as you get older, your lens becomes a lot more brittle. And because it becomes more brittle, this accommodation process becomes much more difficult. It's why for most people at some point in their 40s or 50s, they will need reading glasses, because that accommodation process will hurt your ability to focus up close. If you already have glasses for distance vision, you might need bifocals, you might need trifocals, or you might even need progressive lenses that help enhance a variety of different distances. Okay. Does anybody need some more time here? All right, I'm gonna go ahead and clear those. Let's clear those. Oh, wait. Oh, no. Oh, wait. Oh, that is one of the hard parts about annotation. How do I clear? There we go. Clear all. There we go. Now I feel better. Okay, new toolbars are fun, but it's clear I've got a little bit of a learning curve. All right. So, as I've kind of mentioned, there has to be a perfect relationship between the different components to the eye, and those need to be matched to the eyeball length for things to refract perfectly onto the retina. One of the things that we've discovered is that for a lot of us, either our eyeball is too short or our eyeball is too long, and that creates imperfect refraction. That means that information is not falling on the retina the way it should. Depending on different circumstances, light might be falling in front of the retina, or it might actually be falling behind the retina. So the reason that lenses exist is to basically correct for those refractory errors. And it's always kind of weird the way it works, doesn't it? Now, I've been lucky enough, I have to go to my eye doctor again soon. I haven't had to update my lenses in about 2 years. That makes me nervous. They just keep getting worse and worse. So when I have 2 years where I don't have to change anything, I'm kind of just waiting for the other shoe to drop. So I'm thinking I might need new glasses this year, but we'll see. But let's talk about those different refractory errors. So we have myopia, which is nearsightedness. So a lot of people are nearsighted. That means that they could probably read without glasses. I could probably read something really close to me without glasses. And I'm not actually going to take my contact lenses out because A, I don't have spares, and B, I'm going to have to touch my eyes, and some of you won't like that. But if I took my contact lenses out, I could read up close, but I probably wouldn't be able to see Jenna very easily. And even Lauren and Natasha, who were right up close, might have a little bit of a blur. I kind of started realizing I had problems when I was in my freshman year of high school, and I had to squint every time I looked at the blackboard. And then I realized I was squinting worse and worse. And finally I was like, Mom, I think my eyes are bad. And so that's what myopia is. Myopia basically happens because your eyeball is too long. The different components aren't perfectly matched to your eyeball. So the eyeball is actually a little bit too long. And for whatever reason, light is focusing in front of the retina. It should be landing right here. Especially right here. That's your fovea. That's your macula. It should be landing right here, and it's definitely not. That's why for a lot of us, we have to squint to try to see. Now, on the other hand, if you can see far away, but you can't really see very well up close, you have what is called hyperopia, or you have farsightedness. You can see far away, but you can't see up close. This is a case where the different components and its relationship to the eyeball, in this case, the eyeball is a little bit too short. As you can see, light actually is refracted behind the retina. So these are some different refractory errors that can result when our components are not perfect. Now, one of the things that people have been talking about lately, first of all, we know that eyesight issues do tend to run in families. They do. I'm probably the only one in my family that needed glasses at an early age, like 14. However, as I've gotten older, my sister has needed glasses. Like both of my sisters in their 30s have needed glasses. My mother has needed glasses in her 40s. So these things do run in families. But one of the other things that's been coming up is screen time, lack of outdoors time, lack of sunlight, and getting the necessary vitamin D might also be related to an increase in having eye problems in childhood. I don't know if that's actually true, and that's not me telling me not to take notes on your laptop or not to look at your phone or not to watch Netflix. I'm just saying it's something to think about. Now, I want to talk a little bit about astigmatism. Astigmatism is something that often presents with other refractory errors, but it's a little bit different. So whereas nearsightedness and farsightedness are problems related to the relationship between the components of the eye and its length, astigmatism is almost entirely related to the way that your cornea is shaped. So remember that the cornea is at the very front of your eye. It's filled with fluid, and it's basically designed to help bring light into the pupil, and it helps provide protection to the eyeball. Because remember, folks, your pupils are colored black. Why is the pupil colored black? It's a hole. I think you actually did the same face that I made when I say it, so that was perfect. The reason that your pupil is colored black, it's a hole, and the cornea needs to be able to protect the eye. And the cornea heals itself pretty quickly when it's damaged, even though corneal damage is not fun. But here's the thing, your cornea is shaped like a sphere. That helps create good refraction. We only have one focal point when the cornea is a sphere. People who have astigmatism have a torus or a football shape to their retina. So if you want to be really technical, sometimes it's been described as a football, sometimes it's been described as a donut, sometimes it's been described as a conical shape or an oval shape. It's typically described as a donut. The technical term for a donut geometrically is a torus, T-O-R-U-S, not to be confused with the astrological sign or the Ford car. It's not that kind of a torus. And if you need correction for astigmatism, you get different contact lenses. You get what are called toric lenses. They are designed to basically fit the shape of a cornea that is not spherical. So what happens with astigmatism is because the cornea is not spherical in shape, when light hits, we actually end up getting multiple focal points. So notice here in this example, with the cornea that's spherical, we get a perfect focal point right on the retina. Problem with astigmatism is that because of the way it's shaped, when light hits it, here's a focal point, here's a focal point. Guess what happens when your eye has to resolve multiple focal points? You get a blur. So for a lot of people with astigmatism, they are going to notice a blur. So the example that I've sometimes given is that the lights will sometimes have a halo to them. Everything looks like Christmas. A light has a beautiful halo of light around it because of that additional blur. Those lights are that additional halo. I didn't realize that that's not there. So we get these multiple focal points. One of the things you'll notice if you wear glasses is that if you have astigmatism, if you look at the lenses, one of the things you might notice is that one of them's curved a little bit more than the other, and that's to help correct for the multiple focal points that your cornea has. Now I'm going to hide myself for a minute so that you can see this. Uh-oh. Okay, it is recording me. Okay. This is a pretty common test for astigmatism. So this is not going to be perfect because obviously this is going to be on a screen, but an example of this is in your textbook. So for some people that have astigmatism, when they look at this, some of the lines stand out more than the others. So do some of those lines look a little bolder to you than some of the others? If they do, you might have astigmatism. So this is a pretty common astigmatism test. Okay. So, hey, it could be worse. I could give you all the air puff test. That's not for astigmatism. That's for glaucoma. Am I the only person that likes the air puff test? It makes me giggle. Yeah, I didn't do it the last time either. I was like, no air puff? I'm the only person on earth that likes that.
The person who did it accidentally ejected the little thing into my eyeball. Like, so I do not let people near my eyes.
Oh,
Like, no.
They're like, here, did they have you look at the little house still in the road? How many of y'all have looked at those, the little house and the little road? That's to try to get a measure of your focusing power as well. So I mentioned that the lens does get a bit more brittle with age. Some of you may have experienced how brittle the lens can get if you've ever dissected animal eyes. How many of you are like me and dissected a cow's eye in school? And then you took the lens out and then you got to take it home with you. And then it started flaking off. And that was kind of weird. Apparently, what? I didn't do anything to it. It just dried out. Sorry. Yeah, I was going to say, if you don't like eyeballs, this is not your week. Okay, but the lens does get very brittle and dry with age. And what we're going to see is that with time, as the lens gets more brittle, it's going to lose its ability to change its shape and focus on objects. This is what is known as presbyopia. It is also sometimes referred to as age-related farsightedness. So you get really good close-up vision with a normal eye with a good working lens. In the case of a lens aging and stiffening, you actually will see that because the lens can't focus perfectly because it can't accommodate, once again, we're kind of getting a focal point that forms behind the retina, which makes vision blurry close up. So it's basically causing hyperopia, but it's specifically because of the lens, not because of a refractory error. And one of the things that we'll find, and I'm really sorry to put this out here, it's already too late for you. Hey, if it helps, I'm right here. So one of the things that we know is that when we track people over time, what you're looking at on your x-axis is age in years. We are following 5 different people over the same period of time. We're getting a metric of their accommodation ability. In this case, they are looking at accommodation in diopters. This is something that an optometrist will look at. It's something that an ophthalmologist will look at. But here's what I want you to kind of notice. Here is what accommodation kind of looks like when you're 10. It's pretty good. Here's 20, and it's already dropping. Here's 30. Here's 40. This is basically when it's very, very significant and you might need to have some help. You might need some restrictions on your driver's license. You can see that accommodation ability really just drops throughout life, but it really starts becoming significant at around your 50s and 60s. Prepare for reading glasses. Just be prepared for them. Thankfully, reading glasses are cheap. Yes.
Where's she, the purple one?
He's probably overlapping with some of these because he's right down here at the top. So he's still there, but he's really clustered close with a lot of these other people on this regression line. Why?
Because I want to see where he was and like how he dropped. Because in the first one, he's not even there. He's only the early.
He's up near the top. It's kind of hard to see. There's a little bit of purple right there. Yeah. So this is a case where you can see that this accommodation ability is going to drop very rapidly throughout life. It is already happening to you. It is happening to me. It is happening to everybody. So just plan for it. Just plan for it. Prepare to get some reading glasses at some point. So I want to go back to something that I talked about a little bit last week. So for those of you who weren't here last week, I talked a little bit about the fact that a lot of people really like analogies when it comes to the eye. And one of the best ones is this idea that the eye is like a camera. And that actually makes a lot of sense. Photography is basically an entire field that involves playing around with light to get different kinds of images and get different things that you want. My high school photography teacher really tried to forward that it's playing with light. We even got to do an assignment using the copy machine, because when you make copies, you are also again playing with light. And I had a really cool art project that I wish I could show you, but it no longer exists. I'm so sorry. But there's this idea that the eye is like a camera. So what sort of things do cameras have? They have an aperture right here. So we're talking about an old school camera. So we're not talking about the kind of cameras that are on your phone. We're not talking about digital cameras. We're talking about old school manual cameras, or my favorite, those old school throwaway Kodak cameras that are like really cheap. And when you turn on the flash, it makes as it warms up, those kind of cameras. So we have an aperture. This is an opening through which light enters. And much like our iris restricts the amount of light that can enter the eye, the aperture can grow and shrink to permit how much light enters the camera. Light is going to enter through the aperture, a hole in the aperture. It's going to fall against various kinds of lens elements, and then it's going to make contact with film or photographic paper at the very back of the camera. The film and photographic paper is kind of functioning like our retina in this case. So it's a pretty good analogy. The problem is it's not a perfect one. And part of the reason that it's not quite a perfect one is that first of all, the camera is only recording what it sees. You and I have a whole other set of steps that we now have to do. Not only can we register things on our retina, we have to actually make sense of what we see. A camera can't do that. Its job is pretty much done as soon as that light makes contact with the film or with the paper. Once light hits our retina, it is then going to be sent to the brain so that we can actually make sense of what we see and interact with things. So in that sense, we're not exactly like a camera. Additionally, film and photographic paper keeps kind of a permanent record of that particular shot. In our world, everything is always changing. So what you capture with your eyes at this moment is not permanent. It's always changing. So the analogy ultimately only works so well. The visual system temporarily records the image. There's a reason that we have visual short-term memory or visual sensory memory, and we have to interpret the image that we see. So we've talked about the parts of the eye. We haven't really talked that much about the retina yet. We're going to spend a good chunk of today talking a little bit about the retina and what happens in the retina. Does anybody have any eye doctor related questions for me before we move on? I'm not an eye doctor, obviously. I just go to one a lot. Okay. So here is an image of the retina. You can see that there are a lot of blood vessels making contact with the retina. The other thing that you're going to notice is that here in the retina, we do actually have a blind spot. This is where the optic nerve basically leaves the eye. And you can see that there's a hole in the retina where that optic nerve basically exits. What this means is that you and I effectively have a hole in our vision for each eye. Our brain, now one of the things that I will mention, because of the way that our eyes are shaped, each of these holes occupies a slightly different place in each of our eyes. And thankfully, that means that for the hole that's in my left eye, I can use information from my right eye to fill in the missing image. And the same is true for my right eye. I can use information from my left eye to fill in what's missing. Yes.
Is the blind spot something that's actually able to be seen?
This is your blind spot.
Oh, just
The area where that leaves the eye, that is your blind spot. There are no photoreceptors there. Now, if you're
just like the light when they were shining.
no, so here's the thing, your brain knows that there's a hole in each eye. So it's constantly trying to fill in that missing information. The other thing that kind of helps us, you and I can move our eyes, and we move our eyes a lot, and we can move our head. It's part of the reason why when you're driving, what should you be doing before you change lanes? You should be shoulder checking. Your mirrors aren't perfect. You should always shoulder check before you go into another lane, because you already have a blind spot in your eye. Your blind spot's even bigger when you're driving a car. One thing that I will mention too, that I want to kind of show you in this figure, notice that this portion of the retina is a little bit darker than the rest. This is your fovea. This is where your centermost vision is. This is where your most detailed vision is. This is also where most of your cone photoreceptors are. Another term for your fovea is called your macula. This is going to be really important. We are going to talk about a few eye-related disorders, and one of the ones that we're going to talk about is something called macular degeneration. Macular degeneration basically happens when damage happens to the macula and you basically lose your centermost vision. You are effectively blind for your centermost vision. You have what's called a scotoma, or a hole. And for those who have never had to deal with macular degeneration, my grandfather had it, and he had Alzheimer's. So he still remembered me, but he had trouble seeing me because he had that macular degeneration. Obviously couldn't drive. And I will actually show you a really cool simulation of what it would look like to have macular degeneration. We're going to look at a simulated scotoma later on. So you have a blind spot. Why can't you see it? For the reasons that I've already mentioned. The reason that you don't notice a hole in your vision is because your brain is usually very good at filling in that missing information for you. Remember, Each of your blind spots occupies a slightly different position in your visual field. The fact that they don't perfectly overlap means that information from your left eye can fill in information for your right eye, and information for your right eye can fill in information for your left eye. Now, if you want to notice your blind spot, you're usually gonna have to do things like these. So what you're gonna do, these are in your book. These are very common examples, but what you might do is you might look at something like this, and they'll want you to focus on this little center part that's not colored in. As you pull the book towards or away from you, at some point, this little blank spot's gonna be filled in with the red. And that's how you'll notice your blind spot, because what's basically happening, this has fallen into your blind spot. And you'll have to close one eye for this to work. This won't work with both eyes because remember, each eye is filling in missing information for the other eye. So you can only do this with one eye closed. When you do that and you pull that book away, you're going to know where your blind spot is because it's basically going to fill in this with the missing information from the surrounding area. So I think another example, I think in our general psychology textbook, you look at a car and you look at a dot, and it's when that car disappears that you're able to notice your blind spot. But again, this is only going to work if one of your eyes is closed, because information is always being shared between the two visual fields. This will only work if you close one eye. So let's talk about the retina. We're going to talk about each of these in fuller detail. Now, some of you that have had biopsych and you're looking at information and you're remembering information about bipolar cells and on and off cells and lots of talk of glutamate. And those of you that are currently in biopsych, oh, don't worry, we'll get there. But this is not the class for that. So I'm going to give you a very Cliff's Notes version of how the bipolar cells work, but we're going to talk about each of these in greater detail. So we're going to talk about photoreceptors. We have the rods and cones in our retina. We have our horizontal cells and our amacrine cells. We have our bipolar cells, and we have our ganglion cells. Now, we talked a little bit about action potentials in chapter 1. Action potentials are the electrochemical signals that neurons use to communicate with other neurons. Here's something important you need to know, and I might test you on this. I might. The only cells that I have listed here that fire action potentials are ganglion cells. None of the rest of these actually fire action potentials. They release glutamate based on the strength of stimulation, but only ganglion cells fire action potentials. Yeah, they do. You remember talking about graded potentials a little bit, like we release glutamate based on the amount of stimulation that we get. More glutamate means more stimulation. That kind of idea. But I'm not really going to be very technical about that either. But before we continue, I know it's kind of gross out. I know it's the end of the day. I know that some of y'all get tired. So we're going to do a little activity. I need you to find a buddy. This only works in pairs. So if we have an odd number of people, I will be your buddy. I will not be your buddy rest of the time. I'm your instructor. I can be your friend after I'm done giving you final grades. All right. So have you found a buddy? Who needs a buddy? I was thinking of a movie, Heavyweights, about the buddy system, but he pronounces it body. Buddy! Okay. So does everybody have a partner? Okay, so what I'd like you to do is go ahead and stand up. Some of you might know what we're doing, some of you might not. So I want somebody to have their back turned.
Yeah.
Natasha, you want to come up and help me demonstrate really quick? Some of you have done this before, I know. Some of you, it was last semester. Some of you, it was a couple of years ago. But we're going to demonstrate some really interesting things about the retina today. So, Natasha, you're going to stand with your back facing me. So make sure that you've got this set up. And then what we're basically going to do, you're going to find an object. Make sure that the person with their back to you does not see it. And here's what we're going to do. We're very carefully going to, now, if you've got a height differential with your partner, Natasha and I are about the same size, so this works pretty well. But if one of you is taller than the other, you might have to kind of duck or squat or something like that, but we don't really have to do that here. So we're going to take an object. Natasha, do you know what color this is? Do you know anything about my object? Okay, so what I'm going to do, I'm going to bring it around in front of her eyes. And as soon as you see the color, Natasha, I want you to tell me what it is, okay? Are you ready? Okay. Blue, green. Yeah, it's good enough. Then you're going to switch places and the person, you're going to switch places and do that again. So I'll turn my back. She'll do that with me. So let's go ahead and have some fun.
Also the irony between the cases.
Yes, I'm very, mine's prettier.
I just want to. I'll let you go first. Yeah, well, you have one color.
All right, when you're done, when both partners have had an opportunity to try that, go ahead and have a seat. Okay. I like that exercise for a couple of different reasons. First of all, it gets you out of your seat, plus everybody giggles, partially because you kind of felt like it had to be right in front of your face before you actually saw what color it was. Okay, here's a question I have for you, and this is the point of why I do this. First of all, is there anybody who's never done that with me before? Okay, cool. So some of you have done this with me before, some of you have not. But here's why I do it. How many of you noticed that something was moving before you could actually name the color? Rob, is there anybody who was able to name the color first before they saw something moving, or did you all have the experience of noticing the motion before the color? Odds are pretty good. You saw it moving before you noticed what color it was. And part of the reason for that, don't worry, your visual system is not broken. In fact, by this, it is doing everything it was designed to do. So it turns out your retina is made up of different types of photoreceptors. And it turns out that the photoreceptors that respond to motion tend to exist in the periphery, and the photoreceptors that respond to color tend to be in your centermost vision. So for a lot of you, that object had to get really close to your nose before you realized what it was. How many of you had to have it like right here? Yeah, that's okay. That's okay. You're probably going to notice something moving before the color. Likewise, how many of you have had instances where you can see people moving around you, but you actively have to look at them before you recognize who they are? We're always going to notice motion in our periphery before we notice fine detail because we need our centermost vision for that. Let's take a look really quick at the different makeup of our retina before we move on. So one thing that I want to point out to you is that the very back of the retina is right here. That is the sclera. Now, you've heard me talk about the sclera before because the sclera is also at the front of our eye. It's continuous with the cornea. This is basically the back of the eye. And again, the sclera is what gives our eyes their white appearance. That's why our eyeballs are white, because of the sclera. Now, right behind the sclera, we have an area called the pigment epithelium. And the pigment epithelium is basically nutrition. This is where our photoreceptors get nutrition from. They get it from this pigment epithelium. Now, one of the things that I'll kind of mention that people sometimes bring up, one of the things that's kind of weird about our retina is that light basically goes through all of the cells before going to the back of the eye, hits the photoreceptors, and then gets processed by all of them here. So occasionally people have asked, why does light have to go through all of those layers? Why does light have to go through all of those layers before it can even start to be processed by those layers? And I will say that there are some people who use this as evidence of something like intelligent design. The idea being that, well, this is a little oddly designed, so clearly this is a sign that you and I were intelligently designed by a supreme being or something like that. I don't really know if that's the case. That is like a supreme deity of some kind is a matter of faith, not a matter of science. And we're all about science here. However, there has been a pretty good rationale for why light has to travel through here to get to the photoreceptors. And that's because those photoreceptors cannot be away from the pigment epithelium. If they were up here and processed first, the pigment epithelium needs to be at the back of the eye to make contact with blood vessels and to get the nutrition that it needs so that it can provide those to your photoreceptors. The photoreceptors must be near the pigment epithelium for that to happen. Yes.
What do like animal eyes look like in comparison to this?
Uh-huh.
Are they different, or is it really similar?
The structures are largely going to be similar. The issue is really going to come into play when we talk about photoreceptors. So, for example, we're going to talk about this later when we talk about color vision. I don't want to get too far off track. How many of you have heard the idea that dogs and cats don't see color? That's actually not true. They do see color. Yes.
Is it just limited color?
Yes.
So like dogs see like blue and yellow.
Yes. Like my dog can't tell the difference between different shades of orange the way that I and my partner can. So he has like a chew toy that he really loves that's like bright orange. We call it the molecule because it kind of looks like a molecule. And for a while, we used to have this orange blanket. They were different shades of orange, but if you put that orange toy on that orange blanket, Smedley would be like, where is it? Where is it? I don't see it. And that's because they have a limited color spectrum. They can really only see shades of blue and yellow, potentially indicating that they only maybe have two photoreceptors, like two cones. So the photoreceptors might be a little bit different. I think when we get into different animal species, it does get more complicated. So for example, with birds, they don't actually have cones like we do. They have these drops of oil that kind of work that way. So instead of photoreceptors, so I'll kind of look at some different eye structures and I'll share those if I can find different animal retinas. But I was going to say, if you're dealing with mammals, there might be some differences in the number of photoreceptors or the number of cones for color, but at least for mammals, we know that these are going to be pretty similar. Yeah.
What about bats?
I'm going to look up other retinas. Bats are going to get really complicated because
they scream and that's how they
bats, well, because bats see sonar. Well, and that's going to be complicated when we talk about insects too, because they can see ultraviolet. So I'll try to find what I can, but the take home message is, if you've ever wondered why light has to go through all of the retinal layers before it can be processed, it is because your rods and cones need to be near the pigment epithelium. And this is the only place that the pigment epithelium can be. So we have our pigment epithelium, we have our photoreceptor, we have our horizontal cells, which are going to connect to many different photoreceptors and basically inhibit some of those photoreceptors. We have bipolar cells, which horizontally connect to endocrine cells. And then the bipolar cells will make contact with the ganglion cells. So this is just a way to look at the different layers of the retina. We'll talk more about the functions of each of these cells shortly. Okay, so why are photoreceptors at the back? Photoreceptors are opaque. So that means light can't pass through them. And they're located next to the pigment epithelium, which ultimately provides nutrient for the photoreceptors. So the photoreceptors are always going to have to be at the back for this to happen. My tea bag fell on the bottom of my tea, so I'm going to take out my tea bag because it's getting stuck in my straw. The string fell at the bottom, so now I got to fish it out with my hands. Don't make that face at me, Haley. I'm not. You know what? I'll just dump it later. I'll just drink it this way.
Suffering.
It's too hot for me to reach for it. I'm not going to do that. Okay. We'll just take the straw off. That'll help. Okay. So let's talk a little bit about our photoreceptors. So you have what is called a duplex retina. That does not mean that there is a duplex in your retina. It means that you have two different photoreceptors that are responsible for sending signals to the brain. So we have rods, and here's an image of them. Folks, they are colored blue and pink for your convenience. They do not actually look like this. Huh? That would be kind of terrifying if you cut open a retina, though. You have so many. Can anybody tell me why these are called rods? They're shaped like the outer segment is shaped like a rod. Does anybody want to tell me why this is a cone, called a cone? Outer segment is shaped like a cone. So we have rods and cones. These are specialized neurons. So something really important for you to know, if these die, they do not regenerate. Remember, when neurons die, for the most part, they don't regenerate. There are some exceptions to this, but these do not regenerate if they are damaged. So we have our rods and we have our cones. We have more rods in our retina than cones. So we have about 80 to 90 million rods in each eye. Now I want you to compare that to about 4 to 5 million cones. So we have way more rods than cones in our retina. And each of these photoreceptors are for very specific aspects of vision. So first, before we talk about the functions of the rods and the cones, I want to show you a few different examples. I want to show you where they're kind of located. And we also have some microscopic pictures so that you can see. So here on our x-axis, we have the distance from our fovea. So this is basically our retina going from the temporal retina, which is the outer part of our retina right here, to our nasal retina, our inner half. So that's the outer half of the eye. This is the inner half of the eye. And our rods are represented in blue and our cones are represented in red. Looking at this image, and by the way, the y-axis is photoreceptor density, the number of photoreceptors in the thousands per square millimeter. So looking at this image, what does this tell us about rods? Where do rods tend to be in the eye? Huh? They tend to be in our peripheries, so not just the outer portion of our temporal retina, but also our nasal portion of our retina. So here you can kind of see that they spike in the outer portion of the eye and the inner portion of the eye. Notice that around these parts, there are very few cones though, right? Notice that in our periphery, we don't really have a lot of cones. Here, we have our distance from our foveal center, and notice that at 0, all of a sudden, that's where most of our cones are. Our cones tend to be concentrated in our centermost retina at an area called the fovea. Also, why don't I have anything here? That's your blind spot. There is nothing there. So rods tend to be concentrated in the outer portions of the retina. Cones tend to be concentrated in the inner portion of the retina, particularly around the fovea.
This is the optic, the other optic disc with the lens.
The optic disc is basically where the optic nerve leaves the eye and no photoreceptors exist.
Like what you were saying.
You have, hey, you don't need to apologize if you need to hear something again. You're welcome. Plus, it gives me time to chug lukewarm tea. The point is to drink it, and this thing never cools off, so I have to have it lukewarm. All right. So what this means based on the location, your fovea is where your best vision resides. Your best vision resides basically right around here. That's where your best vision is. So what this means is that your best vision is in your foveal vision, and cones are basically for looking at fine detail. So your best visual acuity is going to be in that centermost foveal vision. Now, your periphery, rods are not, you have many, many rods. They are not for looking at fine detail. They are for noticing things like motion or noticing differences in dark and light. But they aren't sensitive to color. They're not sensitive to object form. So they're not really going to help us out with fine visual detail. So your periphery is going to have the poorest visual acuity. And that's why you will always notice something moving before you can see what it is, identify what it is, and identify what color it is. Because those are the properties of cones. Those are in your foveal vision. Your rods are not designed for that, and they tend to exist in the periphery. It's why, thank goodness, you and I can move our eyeballs around and we can turn our heads if we can't see something. So if I have something in my periphery and I can't see what it is, all I have to do, turn my head so it's in my foveal vision, and congrats, I can see it. And my second reminder today, anytime you're changing lanes, shoulder check. I don't care how much your neck hurts with how much you're driving, always shoulder check. Okay, so here are a couple of different properties of the fovea and the periphery in our vision. So with our fovea, the photoreceptor that tends to reside there are mostly going to be cones. In the periphery, they're mostly going to be rods. Now, we're going to talk a little bit more. If we don't get to it today, we'll get to it on Thursday. Rods and cones converge onto different types of bipolar cells. Rods tend to converge on what are called diffuse bipolar cells. Compare that to the cones, which converge on what are sometimes called midget bipolar cells. I'm not overly fond of that term, but there you have it. Another thing that I will mention, because you have a lot of rods, but you don't have a lot of cones, that means you're going to have many, many rods talking to the same bipolar cell. You could have 10 or even 50 rods converging upon the same bipolar cell. Now you have fewer cones, so you might only have 1 or 2 cones talking to a bipolar cell. This is known as convergence. If you have a lot of something and only so many bipolar cells to go around, you're going to get what's called high convergence. That means a lot of people are talking to the same person. So for example, I'm an academic advisor. I have 22 advisees. For CAUTI, I have very high convergence. I have a large number of students communicating with one academic advisor. Now, compare that to somebody that maybe only has 5 advisees. They're going to get a lot more information from each of those advisees because there's lower convergence. So what we find is that lower convergence means more detail. Higher convergence means less detail. The more convergence that we have, the bigger our receptive fields become. And we'll talk more about receptive fields later. But the more information that you have to integrate, the bigger your receptive fields become. The more integration there is, the bigger the receptive field. Because rods have such high convergence, so many rods are talking to the same bipolar cell. Because we have that high convergence, the fields of view are going to be large. Now compare that with cones that have very low convergence. We don't have a lot of cones. So very few cones are making contact with the same bipolar cells. Because of that, they're going to have less information that needs to be integrated. And as a result, they have smaller receptive fields. Folks, there's a trade-off here. The size of your receptive field is inversely related to how much detail you can have. Big receptive fields mean you don't have a lot of detail. Small receptive fields mean you have a lot of detail. So that's what's called acuity. So foveal vision have small receptive fields, but they have high detail. Compare that to our periphery, where our receptive fields are very large, but they're not very detailed. And then we need to talk about light sensitivity. So something we'll talk more about, if not today, on Thursday. Rods are very sensitive to changes in light. They work best in dim light. So they have very high sensitivity to light. Cones only work in bright lighting conditions. Because of that, they're not very sensitive to light. They have to have bright light so they don't notice changes in lighting conditions. This might be a helpful table to look at. I could see something like this being a test question. To be fair, I haven't written the exam yet. I'm still kind of turning it over, but this could be a pretty good compare and contrast question. Okay, so we're done with those slides. Let me go to, where's the retina? It's there, where? I thought I had it. Wait. It's here. I know it's here. Where are you? I added you. Are you kidding me? Here we go. All right. Okay. So now we're moving from the retina to our brain. So just as a quick reminder, this is actually incorrect. That'll post at midnight. It's due Tuesday at 5 o'clock, but it's going to post at Friday on 12 a.m. It's going to cover chapter 2. Your first exam is coming up. I will post a study guide 1 week before the exam. I think I do have a couple of exams coming up around the same time. So I will try to make sure that I do a review session. Whether or not that review session will either be in person or on Zoom. If it's on Zoom, I will record it and email it to you for a link so that you can look at it when you need it. So if you haven't started reading chapters 1 and 2, it might be a pretty good time to start because the exam's coming up. Okay, so just to give you a recap from what we covered from this past section. So light enters the eye through the pupil. With the help of the lens, it's going to be refracted, which causes light to fall on the retina. You have a duplex retina that contains both rods and cones. Rods are going to be located in the periphery. They tend to be better for dim light. They are not color sensitive. Cones are going to be located in the fovea. They tend to be better in bright light. They are color sensitive and they have very high detail. So cones are going to be for things like looking at color, looking at form, and looking at detail. So now let's talk about what happens when light hits these. So this is probably going to be the most complicated thing we talk about today. We're going to talk about the process of what is called photoactivation. And I'm going to hide these floating controls. There we go. That little bar bugs me. All right. So let's go ahead and talk about what happens when light hits these. So I showed you the picture of the rods and the cones before, but now I want to talk about these different components. And one of the first things that I want to remind you, these are neurons. These are specialized neurons. Now, they do not fire action potentials, but they are neurons. If they are damaged, they do not come back. That's why it's really important to go to your eye doctor. So you can kind of see, by the way, in case you weren't sure that they were neurons, notice down here it says synaptic terminal. It makes a synapse. And notice that like all good neurons, it doesn't touch other neurons. So the outer segment, so the cone part of the cone and the rod part of the rod are near the pigment epithelium, near the back of the eye, near the sclera. And remember that the pigment epithelium's job is to provide nutrition to our rods and our cones. And the other thing that the outer segment gets nutrition from the pigment epithelium, and it also stores visual pigments. These visual pigments are known as opsins. I'm not going to go into detail about what the opsin is for cones, because it turns out that we have 3 different types of cones and they each make their own opsin. However, we are going to talk about, so I'm going to bring back our meaning controls really quick. We're going to talk about the opsin for our rods, which is rhodopsin. That literally translates to the opsin of rods. So it's called rhodopsin. The visual pigment for rods is always the same. It is called rhodopsin. The inner segment is what makes those visual pigments. So they're going to make those pigments, and then they're going to transfer them to the outer segment. And then, as I've mentioned, so we have our outer segment, our inner segment. Hey, folks, you want to tell me what that is? That's a nucleus. It's a neuron. That's its cell body. So you can think of these as really specialized dendrites. Here's your synapse. This is your axon, even though these don't fire action potentials. So we have a synaptic terminal that is going to make contact with bipolar cells. Okay. Did everybody get rhodopsin? It is the opsin of rods.
Is there one for cones?
There, okay, so so I've mentioned that we have 3 different types of cones. So we have a cone, so we have 3 different types of cones. I might be jumping ahead a little bit. So we have cones that I'm gonna be really careful how I use terminology here. Now, if you caught me in any other class, I would call them red cones, blue cones, and green cones. However, your textbook has a certain convention, and it's probably more appropriate than calling them red, blue, or green, because cones that are red cones also respond to orange. They also respond to yellow. They also respond to green and sometimes blue. So it's probably easier to put it like this. So we have 3 different types of cones. We have one type of cone that is maximally activated at short wavelengths of light. So we're going to call those our S cones. If you want to think of them as blue cones, that's fine, because short wavelengths of light correspond to the color blue or purple. But you can, and we're going to call them S cones for this class, because we're going to try to be really technical, because we're going to go into more detail about color vision than any other class. We have our medium cones, or our M cones. These are maximally activated by wavelengths that are medium in length. So medium wavelengths kind of correspond to green or yellow. So we have our S cones, our M cones, and then we have our long wavelength cones. These are maximally active at long wavelengths of light, which corresponds to the color red. So if you want to call them blue, green, or red, that's fine. But if you want to be more technical, they're short cones, medium cones, and long wavelength cones. Each of those cones is going to have its own type of opsin. But we're not going to talk about them here. If you'd like, though, I can try to look up the opsin names for cones. I bet they're long and really ridiculous. Opsins in cones. Interesting. They don't name, most of them do not actually name the name of the opsins. Yeah, they just call them cone opsins. I know, right? Oh, no, it's okay. It's not your fault. I know you're not mad at me. Okay, so what do these photoreceptors have? So one other thing that this figure does not show is that every single photoreceptor, especially around the outer segment, has something called a chromophore. The job of the chromophore is to basically capture photons. Just a quick reminder. This is my reminder to you that light is not just a wave. So we're talking about wavelengths of light. What else is it? It's a particle. And particles of light are known as photons. It is the job of the chromophore on that outer segment to catch photons. And I keep talking about photons, and now I want to watch Star Trek because I'm thinking of photon torpedoes. Okay, as I've mentioned, every photoreceptor has an opsin, which is a protein. The structure of the opsin ultimately determines what light wavelength the rod or the cone responds to. And as I mentioned, all rods have rhodopsin. Now, in contrast, the cones, we're going to go ahead and call those cone opsins. So we have 3 different opsins that are going to code for short, medium, or long wavelengths. That particular cone opsin will determine whether the cone is a short cone, a medium cone, or a long cone.
Something I never get, I missed it, even though you said it like 3 times. You said
Yes. Maximally activated. So a short cone has an opsin that is maximally activated at short wavelengths of light, which corresponds to the color blue. Your medium cones have an opsin that maximally activates at medium wavelengths of light, which corresponds to the color green or yellow. And then our long wavelength cones, they have an opsin which is maximally activated by long wavelengths of light corresponding to the color orange or red. Does that help? All right. How about one more slide and we call it a day? And also, it is 40 degrees. It feels like summer outside. All right. One more slide and we call it a day. You get a picture. Okay, so really quick, what you are looking at here are the different distribution of short, medium, and long wavelength cones in the eye. These are not actually, these have been filled in with color to show you the different concentrations. But as you can kind of see, notice that even in terms of our cone distribution, we have a lot more long wavelength cones than we have medium or short. So this is an example of the different distributions of cones that are in the fovea. So that is all we have for today. I will send you the link to this YouTube recording tomorrow, probably after 11, because I teach 2 classes back to back. We'll talk some more about the retina next time. Have a good day, everybody.